now we can pass on to the next and last presentation of this session one. This will be done by Margarita Stancheva from Bulgaria. Are you here, Margarita?
Yes. Okay. Yes. Thank you very much, and good morning, everybody. I'm now checking to share my presentation. Okay. So have you see it in a presentation mode? It's okay?
Yes, perfect.
So, first of all, I would like to thank you very much to the organizers for inviting me to this great event dedicated to the International Women's Day. I'm really delighted to be with all you here. And I'm going shortly to present one study focused on coastal erosion and land-sea interactions, which are caused from the coastal erosions, but in the perspective of maritime spatial planning. Just a short introduction of myself. I'm director of the Center for Coastal Marine Studies. It's a new organization established in 2018 in Varna, Bulgaria, on the Black Sea coast. I have a PhD in oceanography, but I specified mostly in coastal geomorphology, coastal processes, shoreline changes, coastal erosion, and in the past 10 years I also worked a lot in maritime spatial planning, also sustainable coastal development, blue economy, and many other new European Union initiatives. So first of all, okay, so I tried to change the slide and I was out. It's very strange. It's okay now? Okay. Okay, great. The study that I'm going to present today is actually part of the already ended Mars Plan BS2 project. It's a cross-border maritime spatial planning for the Black Sea, including 2 EU member states, Bulgaria and Romania. It's funded by the European Commission's DG Mare and SINE through the European Maritime and Fisheries Fund. And it's aimed to support directly the competent maritime special planning authorities in Bulgaria and Romania, which are 2 ministries of regional development public works, for the implementation of the EU directive on establishing a framework for maritime special planning. So in the project, our Center for Coastal Marine Studies led a special task focused on developing relevant methodological guidelines, how to analyze and how to integrate the land-sea interactions in the maritime spatial planning, and how these methodological guidelines could be used as a guidance for the next stages of the maritime spatial planning as repetition models that could be applicable to the national MSP plans for Bulgaria and Romania. So first of all, why we need to analyze land-sea interactions in maritime spatial planning. It is well known that most maritime activities are actually, and coastal activities are actually closely interrelated at the border of land and sea, both in terms of human activities and in terms of natural processes. For example, many maritime activities also have a terrestrial component, such as shipping sector, which needs ports or grid connections, but as well as many natural processes are interrelated, and the land-sea interface, for example, accretion, erosion, which are caused by sea currents, waves, and weather events. So in this way, human activities and natural processes interact in a complex way along the land-sea interface. So starting with the scoping of these tasks for elaboration of methodology for land-sea interactions, we identified that we actually miss in the national legislation of Bulgaria and Romania a specific definition for the land-sea interactions. Because although the concept of land-sea interaction is not completely new, it is still unclear for many planners, decision and policymakers how to implement this in the context of the maritime spatial planning, how to apply it. And this is because in the perspective of the maritime spatial planning, the land doesn't mean only to identify the land-sea interactions issues, but also to integrate them practically in a way that to relate both coastal and maritime special planning authorities, also authorities responsible for the management of different land-sea interactions, and to integrate them to govern with their responsibilities and mandate to govern the land-sea interactions at national level, but as well as cross-border and transboundary level. So the first task in our activity was to set up common analytical conceptual framework to analyze the land-sea interactions and to set up a common definition. So we established a four-dimensional conceptual framework which actually considers the land-sea interactions in a two-way perspectives, looking from the land to the sea, but as well as looking from the sea to the land. And this conceptual framework includes interactions which are related to natural biogeochemical processes, as well as their interference with human activities, both on the land and the sea. Second, interactions between socioeconomic uses and activities at the sea and at the land, but also considering their impacts on coastal and marine environments. In this framework, we certainly included governance and spatial planning systems, institutional frameworks that are related to the management of various groups of land-sea interactions, and MSP process related aspects that are very important for the integration into the maritime spatial planning. So the land-sea interactions is a common, this is our definition, is a complex phenomenon that includes both natural processes, but as well as socioeconomic uses, activities, which includes also environmental factors in both directions, land, sea, and sea land, but as well as arrangements, different government frameworks for managing these land-sea interactions and possible ways for their integration into the maritime spatial planning. As you can see from the framework, the stakeholder involvement is a really crucial and critical component, as well as temporal dimension. So these are the horizontal, vertical, cross-cutting linkages to the entire conceptual framework. So coastal erosion actually represents one of the most critical land interactions for the Bulgarian Black Sea coast, in particular, which is predisposed at some places from the geological and lithological structure. And this is a very critical issue, in particular in urbanized places which build tourist infrastructure, especially in the northern, on the northern coast of Bulgaria. So coastal erosion can generate impacts both on marine, coastal environment, as well as on human activities. One of the key impacts are, for example, coastal alteration in result of different infrastructures, constructions, for example, coastal protection structure that stop the sediment transport and cause loss of sediments or degradation of habitats. Also negative impacts on natural resources, ecosystem services, and loss of habitats, which consequently influencing environmental fragmentation. They cause loss of biodiversity, landscaping, and environmental heritage. Impact on human activities are mainly on tourism development, but also on fishery, transport infrastructure, and physical restructuring of the coastline. So in implementing and testing the suggested methodology for lens interaction, we actually elaborated a specific case study focused on coastal erosion-driven lens interactions as one of the key issues that was selected for the involved stakeholders in the testing the methodology. So our study is focused on these coastal erosion-driven lens interactions in the northern part of the Bulgarian Black Sea coast, in one municipality, in the cross-border area between Bulgaria and Romania, Shaba municipality, where actually the highest rates of cliff erosion occur. So the Bulgarian Black Sea coast is located at the western part of the Black Sea, between the border of Romania on the north and border of Republic of Turkey to the south. And in this study, we actually performed an analysis of the shoreline movement at sandy beaches, and we explored erosion aggregation processes and cliff retreat at rocky coast, applying the digital shoreline analysis system, which is a GIS extension modeling tool for this type of analysis. So we didn't investigate the entire shoreline in the study area. Instead, we selected 7 representative sectors, including 3 sectors of large sandy beaches with large sand dunes landward, and 4 sectors of loess type cliff that are most prone to erosion. What regards to the coastline classification, first of all, we derived the length of adjacent coastline from very high resolution orthophoto images from in 2019. As I mentioned, it's my type of sandy beaches, but as well as from coastal cliffs, as 10 kilometers of the coastal cliffs is presented of loess type cliff. And actually the coast is with eastern exposure, it's straight. It approaches by the strongest waves from east, northeast, southeast direction. At rocky coast portions that are made by loess, they're actually cover upper Sarmata limestones, and this specific lithology predispose an intensive coastal erosion process. There are also very few coastal defined structures comprising total length of 1.38 kilometers in the study area, groins, coastal dikes, some riprapes, and 1-2 sea walls. So we use different type of data for this specific study. Topographic maps in scale 1 to 5,000 from 1970 to 1975, and orthophoto images with very high resolution from 2006, 2011, 2019. And we use also 3 different calculation methods for shoreline changes at sandy beaches and cliff retreat at rocky coast. So these are the net shoreline movement, which reports the distance between the oldest and the youngest shorelines for each transect. The endpoint rate calculated by dividing the distance of shoreline movement by the time elapsed between the oldest and the most recent shoreline, and the linear regression rate of change for shoreline position determined by fitting a least square regression line to shoreline points for a particular transect. So for our case study, we selected a spacing interval of 10 meters for all transects along the coastline in order to capture all the particular shoreline changes and cliff retreat changes. So these are very shortly, very briefly, the results from next shoreline movements at 7 representative sectors: sandy beaches and rocky coasts. These are the middle-term trends of shoreline change derived from the linear regression rate for the sectors with 3 large sandy beaches, and results for cliff retreat analysis at 4 rocky sectors. And these figures are represented the shoreline changes, which are analyzed with the digital shoreline analysis system, and the middle term shoreline B changes between 1970 to 2019 were registered with a trend of creation in 2 of the 3 study sandy beaches, while at the northernmost beach we registered very minor minimum coastal erosion. And these are figures representing the analysis of sectors with rocky coasts, cliff sections consisted of lost sediments, and the average rate of cliff recession here was measured minus 0.19 meters yearly between 1972-75 2019, with the highest rate of 1.76 meters yearly for cliff retreat, which was registered at some of the coastal transects in Sector 6, and the maximum net cliff erosion for this middle term time scale that we explored was measured about 82.71 meters. An important goal of our study was also to identify the areas with the highest rates of coastal erosion, in particular on cliff sectors. So this figure shows the existing built environment protected areas in the study area versus identified coastal erosion hotspots. And this way it is possible to visualize where the erosion is posing the highest risk to different infrastructures, public, private properties, roads or agricultural lands, or natural environment. And actually, most of the current issues in the study area has resulted from the poor planning decisions in the past that permitted construction of private homes, roads, infrastructure developments in the most coastal erosion-prone zones. As shown on this photo, and of course without providing the required setbacks, the buffer zones to provide this mitigation of coastal floodings and sea level rise. For years in Bulgaria, as in other many countries, the coastal protection measures mainly consisted of hard protection solutions, including solid groins, coastal dikes, and as a result, the Bulgarian coast is almost 17% of the Bulgarian coast has been armored in result of all these hard protection structures. However, these conventional methods, although effective at some places, they come very often with certain adverse effects, and apart from their high maintenance and construction costs, they also tend to result in further erosion and provoking also degradation of coastal ecosystem services at many places along the coast. So in our case, as the study area is low urbanized and still low developed, this also promotes more naturally oriented protection measures and solutions that we recommended to the planners. For example, do nothing option at places that are with low cliff retreat or without built infrastructure or private homes, farmland, and so on. So in this case, recommending do nothing option, we actually allows for the cliff to erode naturally, to continue to erode naturally, and to evolve by a natural mechanism. At the same time, cliff erosion is one of the main nourishment sources to the adjacent beaches as well. So possible alternatives that we recommended also include nature-based solution as building submerged reefs at those portions with highest cliff retreat. So this is one modern way to reduce adverse impacts of erosion by creating healthy ecosystem, by engaging natural processes, and thus providing really sustainable, cost-efficient, ecologically sound option for protecting the coast against erosion. So then our conclusions and recommendations for this specific study are first of all to the coastal managers and maritime special planners. So it is critical to minimize the uncertainty of shoreline measurement by using high quality data and a consistent protocol. We identified that if in the study area there are not any significant human influences in terms of building other solid coastal protection structures, so the future short and middle term trends of positive shoreline movement as well as cliff retreat rates will remain similar to what have been found in our study. And we recommended at the end detailed coastal monitoring program that should be conducted in the study area to document and to record the sea level rise changes, as well as present location, conditions on cliff and bluff edges, also delineating armored and unarmored sectors of the coastlines, and identifying these hotspot erosion areas. And this in turn will provide robust background for future decision making and more adequate land sea interactions management, both in terrestrial and maritime spatial planning. At the end, I would like to thank you very much for your attention, and you can find more on this specific study published in the Journal of Coastal Conservation. Our peer-reviewed research paper focused on these coastal erosion-driven land sea interactions. And also, you can find our results on the Maritime BS2 webpage to find out more on the suggested methodology for analysis of land sea interactions, testing and application of this methodology in Shabla case study area, and report on best practice recommendations how to further work on integration of land sea interactions in the maritime spatial planning. Thank you very much for your attention.
Thank you very much, Margarita. That was a very interesting and comprehensive presentations. There are time for some questions, please.
Moni, this is Susan here. Just in the chat, Themios, I know his voice is not working, so I'm going to read his question because
Okay.
I know he's got a very bad voice. So he congratulated on your presentation. Thank you very much. Did you take into consideration errors of shoreline change estimations according to the resolution of the source data, maps, aerial photos, etc.?
I'm sorry, according to the resolution of?
The source data. As in, for example, maps, aerial photographs.
I understand. Actually, for the shoreline positions, we referred only to wet dry line. So these were for the sandy beaches, and for the cliff retreat rate of change, we referred to the edge of the cliff position.
So that was from the aerial images?
Yes, from the aerial images and from the topographic maps. So we compared different type of sources to accurately and precisely actually define the shoreline changes and cliff retreat change.
Thanks. And if Monica allows me, I have a follow-up question.
Yes, please.
then, so you used aerial images, and thank you for those clarifications on how you defined the shorelines. That's very nice.
Okay, yes, I understand. It's difficult because, you know, we assume that the shoreline change uncertainty is very low in our case, because, first of all, we used aerial, these weren't actually aerial, but orthophoto images. So these are not usual aerial images, but orthophoto images, which are with very high resolution, as I showed in the slide for data and methods. So actually, we do reference these orthophoto images, and we assume that the error from calculations are very small because we used only modern sources of shoreline position, of coastline position, topographic maps, and orthophoto images, as well as the error from georeferencing is also assumed very small. In addition, the Black Sea is almost tideless, so the diurnal variations are at least 8 centimeters. So it was easy to follow accurately the shoreline position in this way.
Thanks. Thank you very much.
Thank you. So I see that Clara Amaroli has a question for you. Clara, please.
Okay.
Okay, yes, thank you, and congratulations for the very interesting presentation. And I would like to ask you, for the monitoring of the coast, are you planning also to exploit satellite information, even if the resolution is much lower, of course, but for a more frequent, let's say, monitoring? Thank you.
Sure. We actually recommended this to our competent MSP authority and to coastal planners in the Shabla municipality. But I assume that, of course, it is included in the draft Maritime Spatial Plan of Bulgaria and in Romania, that all types of information and new modern data, including this satellite data, Copernicus platform, etc., will be used for the monitoring of the coast, and they're, of course, included in the planning as reasonable, as valuable, and a really good way to provide this monitoring in the future.
Thank you very much.